This screencast is about polarity. Polarity is when you have an uneven sharing of electrons. And it is easiest to see polarity whenever you have the Lewis structure drawn out. But you can also calculate it. So we can either have the Lewis structure, or you can look at the electronegativities. You may recall that electronegativities have an increasing trend across the periodic table. We become more electronegative. And as we decrease down the periodic table, we become less. So this is more, and this is less electronegative. And so fluorine is an exceptionally high electronegativity, and cesium is a low one. If you notice this water molecule would be in the shape of bent. It is not a linear molecule. These lone pairs cause the hydrogen-hydrogen bonds to move closer to each other, and this is not, it's in roughly a bond angle of 109. So what is happening here is that these electrons over here on the oxygen have a repulsive power that is different than the hydrogen's bond. Okay, so they are going to have a different ability to push this molecule around. So we are looking for uneven shared electrons on a molecule. Okay, so if you look at this particular structure, if we look at the symmetry, we will be able to determine if this molecule is symmetrical and the electrons are evenly dispersed around the center, or if it's uneven. So if it's uneven, we are going to call it polar. And if it is even, we will call it nonpolar. Okay, and what is happening here in this water molecule is we might have, we kind of have a symmetry this way, but if you look this way, we do not have an even distribution of electrons. So this water molecule is polar. That's one way to determine if a molecule is polar or nonpolar, simply looking at the Lewis structure. The second way to determine is by looking at the electronegativity difference. So if you look at the periodic table, as I mentioned earlier, the electronegativity, this is a high electronegativity, and this down here would be low electronegativities. Another thing is this side is mostly metals, and this side is mostly nonmetals. In general, and always, when you have a metal combined and a nonmetal, you will have an ionic compound, because you have gained or lost electrons. That can be thought of as a polar, because the electrons are not evenly distributed. When you have two nonmetals, you will have the potential for a polar or a nonpolar molecule. So if your electronegativities are pretty different in the magnitude of 0.4 up to 1.7, these would be polar. If your electronegativities are between 0 and 0.3, these are nonpolar. In the case of water here, you can look at it and you should be able to recognize that the hydrogen is on the far left side of the periodic table and the oxygen is on the right side. And they should have pretty different electronegativities according to the trend. And so therefore water is also going to be listed as polar. Alright, so looking at these two molecules, you might be asked to decide if they're polar or nonpolar, and then to decide which way the pool would be based on the positioning of the electrons. You also could be further asked to label the direction of the polar bond. Okay, so let's break it down into a couple of things. Let's first decide if these are polar or nonpolar. So if we're looking over here at the NF3, and you can see that the Lewis structure is drawn, and it has all the lone pair electrons drawn. If you look at this molecule and you ask yourself, Are the electrons evenly distributed the whole way around in the same numbers and spaces? And you would say no, this is a polar molecule. If you look at each fluorine has 6 electrons that are unshared and have their full repulsive power. And this nitrogen only has 1 pair of electrons. So if you thought of it as almost like a tug of war where the fluorine has the power of 6, each one of them, and the nitrogen has the power of 1, you're going to, or 2, you're going to see a decidedly uneven tug of war game. You're going to see that this molecule pulls in a downward direction. Okay? If you come over here to the CH3F, you will also notice that this does not have an even distribution of electrons. The hydrogens have no exposed electrons, where this fluorine has 3 pair or 6 electrons. So this entire molecule would pull upward, and this is also polar. You might be asked to label the partial negative or the partial positive for the molecule. And what they're asking you to say is, where are the electrons? Where the electrons are located will be labeled as partially negative, and the lack of electrons would cause it to be partially positive, because the electrons in this bond here are being shared evenly between the carbon and hydrogen, but they're being pulled slightly towards the fluorine. So in this molecule, the CH3F, we would label the fluorine as partially negative, and this side we would label as partially positive. And so we use the symbol sigma and then the positive or negative to indicate what the partial charge is here. You can do that for each bond. Another way to label the polar bond is to indicate the direction of the electrons by making an arrow where the pointy end or the arrowhead points towards the negative, and then the back end of the arrow looks like a positive sign. Okay, so you would do that for each bond. That would point the direction towards the electrons. Okay, so in the NF3, we are showing that each one of those bonds are polar and they're pulling towards the fluorine. In these two molecules, you can be asked if the bonds are polar and if the whole molecule is polar. If we look at the carbon-hydrogen, the CH4 on the left, we could say that each one of these bonds is slightly polar because the hydrogen has no electrons of its own and the carbon would be the one that would be having the electrons towards it. So each bond in the CH4 is slightly polar, but the whole molecule is nonpolar because they cancel each other out. You have 4 equal and oppositely charged or pooled bonds, and so there is no net pull, so it is nonpolar. Also over here in the CO2, you can see that both of these bonds, these double bonds, are being pulled with the same force towards the oxygen and away from the carbon, but they're also canceling each other out, so the whole molecule is also nonpolar.